Nice, nice, cool. So another cool thing that I haven't actually tried this with the programs that we have on here, but if rather than just diverting it to say that you win, if you wanted to take it to the next level per se, you could find some shellcode online, which if you go look up Smashing the Stack for Fun and Profit, he's got like a big thing that's just got a lot of shellcode in it. And if you use that in your string, you should be able to get a shell on this computer by the same general purpose. You'd have to guess where the buffer is, though, which takes a little bit of time. But if you use like GDB, it's all good. It works totally fine, totally fine. All right. Oh, yeah, here, I've got some other examples, too. Let's check those out.
Or your client needs to give up its connection. Nice shadow file.
All right, so I also have, I wrote out just like a couple of examples just to kind of take a look at. I didn't run them or anything or try to attack them, but just to kind of see what other cool things exist. So in this one, exactly what basically I gave you guys. It's a buffer, and you write into it, try to own it by guessing the start of the buffer and everything. Pretty simple, pretty awesome. All right. So this one is a little bit different. Does anybody happen to guess to see how this is vulnerable? Does anybody have any sort of clue? And it's real subtle. You gotta like really look for it, but it's there. And this is why I think these are so cool, is because a lot of these hinge on the fact that you have to really kind of look for the small subtleties that someone may have forgotten. Basically, this function copies len characters into the buffer, and if it checks to see if you give it anything that's bigger, and it says, I'm only doing that many. And so you would think there's like, oh no, all hope is lost. You look like you have an idea.
Is it integer overflow?
No. No.
Or under, okay. Well.
No, also not that. But it's definitely there. It's like one character will give it to you. Like, anybody? Do you want me to tell you? All right, I'm going to tell you. All right, so this right here is what's gonna spell death for this one right here, because this is copying not len, but len plus 1 characters, since it starts at 0. And you may think that that's kind of like not that cool, but you got to think about what it's overriding if you do give in 1 more character than it needs to. So you remember that there is a frame pointer right before the return address. And so also, if you will recall, x86, little endian. So that byte is the least significant byte of the frame pointer address. So you can then overwrite the last little bit, point the frame pointer back into your code, and when the function returns, it's going to move the frame pointer into your buffer, which then you can have a return address sitting next to it because it thinks that it's the frame pointer. I could draw that. I'm going to draw it because it looks cool. So yeah, you have your buffer, then you point the EBP back here, and then you put a return address here, but like the real one is like here. And like this is where you're overflowing. You got some other stuff here. But like, yeah, so when you point it back into here, this is all the buffer that you originally controlled. So it's just going to think that that's where the return address is. So off by 1. It's kind of cool. I think that's awesome. I don't know. All right. And then finally, I've got one more. All right. Happen to guess? Anybody? Anybody? Anybody?
control the size parameter.
Yeah.
So you can just copy a bunch, or 100 plus. You just pass in
Yeah, so
108.
make the size less than 100, and then make the character string faster.
Yeah, you have to make it less than 100.
Oh.
It's got to be less than 100. Anybody? Richard? Do what?
Does mem copy?
Yeah, okay. Yeah, this right here is it's treated as an unsigned number. So you can pass in a like a negative number, and this will pass, no problem, but this will be a huge positive number. So, again owned. So, yeah, there's ways you can figure out, how much so that you can write just the right number of bytes, but, two's complement. Who would have thought, right? Yeah, so that's exactly right. I was thinking you were going to get it because you said that earlier. That's called an integer overflow or underflow, whatever you want to call it. But when you wrap it back around or treat it as an unsigned, it will work. But yeah, those are the three that I have. Good work, guys. You did it. All right, let's go back to here. All right, I'm also, since, I got time, I'm going to talk about other stuff too. It's going to be cool. All right, cool. And I don't actually have any slides for these, but I'm just going to talk because talking's fun. So there are these are just like really basic types of buffer overflows. There's like the ones that you would actually see happen now are like way more intense. They're in like random functions that are like, yeah, this function renders this image for like the file explorer, and like for some reason there's a buffer overflow in that, and someone passes in a malicious picture and it does it. Like they're really intense now. Specifically, I've seen a couple of really cool ones. There's one called a double free vulnerability, where basically if a programmer accidentally frees the same amount of memory 2 times, it gets you access, or it will let you overflow, because the way that free works, it keeps like a big list of blocks that are free. So if you free the same one twice, it like points back to itself. So then the next time that you use it, you can overwrite those pointers and write shellcode into that, and it totally works. But the best one, and this is the printf one, because I never thought that would even be like a real thing. But you know how in printf you pass it format variables like the percents, all the percent things that are like, %s, and that'll print a string, or like, whatever. There's a weird one that's %n, and what it does is all the characters up to the %n, it counts that number of characters that is printed out, and it writes that number to memory. I don't know why. Like, I don't know any sort of reason why printf would need to write to memory, but it does. And the way that printf keeps track of all of those format variables is by putting them on the stack. So it'll just start writing characters to the stack, or writing numbers to the stack, and you can just use that to write return addresses into the stack, which is kind of, but those are like really hard to do, because you have to, count like, I need 1,000 characters here because I need a number 1,000 right here, and then you put a % after that, and you do like 100 more, and then you do another one. And yeah, I never thought that would even be a thing. Who'd have thought? I don't know. So yeah, now that we've talked about those, let's talk about how to stop it. Rejected. So there are some protections put in place by the operating system. For one, ASLR, address space layout randomization. A lot of the big reason why buffer overflows work is they can guess where their buffer is going to be. This makes it where you cannot. It basically takes all the segments, like the code segment, the data segment, and it just picks random places and it like puts them all over. So that way, every time you run it, it's like you're never going to know where your buffer is. So it makes that pretty hard to do. Makes it pretty hard. For the demo, we had to turn that off because, like, haha, if we had left it on, that'd have been pretty funny. But yeah, so that's a pretty good technique. And all these techniques are not necessarily, like, there's still ways around a lot of these, but they're trying. It's really hard to fully just say like you can't execute on the stack or something because like there may be some random corner case that all of a sudden you need to, and you're like, well, I disallowed that, and it's like, sorry, bro. Another one is StatGuard. The GCC has this thing, so when you compile a C program, it takes, unless you tell it not to, it takes like random values that it computed, and they call those canaries because of like mine shaft, and you know, like mines are cool. And so they put these canaries into the stack, kind of like right before the return address. So when you go to write to memory, it's going to start writing, and it writes over that value. And then when the function returns, it's going to check. It's going to like call another function that computes the canary value, and if it doesn't match, it knows that it got tampered with, and you'll see like a big warning, be like stack smash detected, and you can turn that off, but would not recommend doing that. That would be pretty bad. And some compilers actually place buffers at the end of all the variable lists. That way you can't do that local variable pointer hijack stuff. It'll like make it to where you can't do that, even though it doesn't really do anything for the actual like writing over the return address because it's still right there. But it does stop the local variable hijacking, which is good. It's good. There's another thing called libsafe, which is like it looks at the two saved frame pointers and it calculates the distance between the two, and then it checks the amount of bytes you're about to write, and if that's bigger than like the frame itself, it'll say like, hey, that's probably going to be bad, so don't do that. So that's also good. And yeah, that's all I got. We got any questions? Any questions from anyone? Cool. Yeah. All right. Well, that's what I got. So yay.